Thank you very much, Marcus. Thank you very much for inviting me here. I'm very happy. And today I will tell you about a simple problem that we finished past year in an effort to understand what happens with twisted bilayer of magnets in the context of this twisted bilayer graphene, etc. So what's the purpose of the work is try to find sources of chiral fields, intrinsic chiral fields in systems. They usually are attributed to Jaroczynski-Morilla type of interactions, but they also can also arise from dipolar interactions because both of them essentially connect the lattice with the spin in some anisotropic manner, right? So, for instance, this is a simple system of dipolar clusters where dipoles live in the site of these clusters, and they have some altitudinal degree of freedom. So dipoles live out of the plane, and they rotate around the center of each cluster. And when you replace magnets with such an anisotropy plane in this dipolar interaction for those clusters, you get that for cluster with even number of sites, and also for cluster of odd number of sites. What happens actually exactly is that the magnetic dipolar energy can be separated into symmetric type of interactions and also anti-symmetric type of interactions. And those ones that arise exactly in these clusters actually are responsible for the magnetoelectric effect in this type of systems, where essentially polarization, electric polarization can be attributed, can be produced due to magnetic fields, and this is because you can essentially expand the free energy in terms of electric field, magnetic field, and if you allow higher orders, you find this tensor here, and this tensor breaks time and inversion symmetries, and it happens in systems that satisfy that, and this is one of this case. So one of the reasons also for finding this trying to find systems where these chiral fields arise intrinsically in the system is because this magnetoelectric effect can also arise. So, so these are also some toroidal orders. They manifest in natural materials, are also in some artificial nanomagnets. Essentially, this is what is called like a ferrotoroidic type of order, like this one, for instance, where spins essentially arrange in little vortices with some helicity if you want, or you can also define something that is called the toroidal moment, which is defined in this way in coarse grain, or this in the continuum. And in some places of the lattice of these artificial lattices, and also in these materials, there are some domains where these toroidal moment have some points along z direction, and in the other around -c. There is some domain walls. It's very interesting, and you can understand that from the free energy of the system, which you can expand in terms of gradient of the magnetic field, and the terms proportional to these quadrupolar moments here is what is called toroidicity. Okay, so it can arise from orbital and spin moment, and what I want to tell you that actually it arises in a very simple system also, and now this is a bilayer system. So the most simple of all the lattices, a square lattice, where there are some So two lattices, one lattice, the other one I will call mu, the other nu. The lattices have at the sides dipoles, and these dipoles can rotate in the plane of the lattice. So they have a easy plane anisotropy. These are point dipoles. Okay, this is the dipolar energy of the system, where mu and nu means the different layers, and I and j means the different magnets. Okay, this is the energy scale, which is the dipolar energy between nearest neighbor magnets, and is proportional to the intensity of the magnetic moment, mu naught, etc. And the lattice constant. So this is the magnetic moment. If I place the same other layer on the top at some distance h, now I can place my z-axis like out of the plane of the lattices and rotate each of them in an angle theta. This angle theta is not anything, it's an angle that we are going to call a Moret angle. Okay, and it's defined in terms of two natural numbers, p and q. And when we rotate one lattice respect to the other in such a way, a Moret pattern is going to arise, in which if the original lattice vectors were a sub I and a sub j, or a sub 1 and a sub 2, now the new Moret pattern will have new lattice vectors. Okay, so for instance, here are 3 examples for different angles. This is for an angle 8.78, 22.62, 36.87. So you can see that depending on the angle, a different Moret pattern is going to arise. Okay, so this is the new vectors now. So if we start, we just place one lattice on the top of the other without rotating. You know, Henley found the ground state of this system. Each lattice ordered in an antiferromagnetic zigzag patterns. That means, for instance, the mu lattice, which features spins in blue, will have rows of ferromagnetic collinear magnets, which communicate antiferromagnetically with the other row. And so if we have one layer like that, and we place the other layer below that, the only thing that will happen is that the second layer will couple antiferromagnetically respect to the previous one. So this is like the ground state of the system when there is no twist. So the zigzag antiferromagnetic order and antiferromagnetic one layer respect to the other. But as we start rotating the layers one respect to the other, we can also change distance. So these are the results of molecular dynamic simulation, also energy minimization to contrast. So these are the spins in real space, blue for top layer, red for bottom layer. And this is a density map of the z component of the toroidal moment, okay? For different values of h, the distance between the layers and the angles, okay? So we define, before I explain this, 2 order parameters. So there is this T super AF, which is like a stagger toroidicity in the system. And this is like a zigzag toroidicity. That means that different chains have the same toroidal moment, but between them they couple antiferromagnetically, and this is like a staggered direction of the toroidal moment. So here, yellow and blue points essentially means the direction of the toroidal moment, which can be out of the blackboard and in the blackboard. So we found 6 phases changing theta and h. The first two, we call them like Elise. They have helical orders. Okay, you can see these features. This is in yellow is the Moiré unit cell. Okay, and the other is the magnetic unit cell. You can see some domains here. A large number of spins, comprise this pattern. So this one is different from that just qualitatively in the sense that it has more spins. And then we found these toroidal zigzag and toroidal antiferromagnetic phases where we have these rows of cells, of clusters of spins with the same toroidal moment along rows and antiferromagnetic between them. And this, we have this staggered pattern, okay? For different values of theta and h. So essentially we have, for all of the angles, this is 45 because of the symmetry of the square lattice, right? We find that in this region of height, the system doesn't order, or many orders coexist. It's not easy to find any pattern. But for small distances, we have an helicoidal phase here for small angles, and then we have this toroidal zigzag phase. And then as we go to higher, to larger separation between layers, we have this helicoidal phase here and this toroidal, and here we go back to the zigzag original state and then a toroidal phase. So we can also examine how the system transits from one to the other. So in terms of h, for some angle, for instance, 36, okay, we can study the toroidal order along zigzag chains and the antiferromagnetic toroidal order parameter, and we see that they cross here at about 0.7 or 0.75, okay, and this region here, they coexist. We cannot find any order on this. And then we have this antiferromagnetic pattern. So, so what is happening in the system? So essentially, we can study what is the magnetic field that one of the layers produces in the other layer. For instance, the mu layer is going to induce in the new layer, or spins in the new layer will produce a magnetic field in spins in the new layer, which is going to look like this. We can separate two sublattices, okay? At zero twist, this is going to be essentially what will be the magnetic field. We can essentially approximate to the continuum, and we get that the x and the z component of the magnetic field at zero twist cancel out when one just compute this magnetic field, and we end up with a staggered magnetic field along the y direction. So there is the internal field of one layer on the other, in the position of the other is just along the y direction, once you sum all the interactions, all the fields. Okay, so at zero twist, the torque that the new layer, for instance, induce in magnets of the new layer is going to be 0, because the magnetic field is essentially collinear with the magnets of the other layer. So, but what happens when there is a twist? When there is a twist, two things happen. The first is that the magnetic field is a vector, so with a twist, it changes as a vector. So B prime, right, after the twist is going to be the original B plus theta cross B, right? But also, the magnetic field depends on vectors. So the vectors, right, are going to change also with the twist. in such a way that at the end, the twisted magnetic field, okay, which have, like, as an argument, twisted vectors are going to change in this way. So overall, the infinitesimal change in the internal magnetic field due to twist is going to change in this manner, right? So when we evaluate this, we found that the magnetic field actually have now a new component, which is an X component due to this parallel transport, okay, which is proportional to the twist angle, okay? And then we can compute the torque now on the magnets, and we have that this is the torque induced due to twist, which also depends on age through the field. Okay, so this is the intensity of the magnetic moment, the angle, and this is the magnetic field at zero twist. So, and one can also do a gradient expansion of the free energy of layer mu, right, in the inhomogeneous magnetic field, which is created by dipoles in the layer nu, right? And one, we have that the free energy is the original free energy without a twist. And there is this term, which is proportional to the staggered magnetization multiplied by the twisting magnetic field. And there is this term here. And this term is proportional to the toroidicity of the system. And from that, one can get essentially the conjugate field to the toroidal moment in the system. So is this field, which is conjugate to the toroidicity of the system, which couples, okay, to the toroidal moment, and actually is the responsible of twisting and creating these chiral textures in the system. With that, I leave you with the conclusions. So we have toroidization can be induced by a twist, and it can be tuned by H and theta. Twist between layer triggers a net magnetic torque orthogonal to the bilayer system, and it leads to new magnetic orders. New magnetic phases are magnetization free. They break time and inversion symmetry and depict chiral motif. Okay, that realize these toroidal moments, and the conjugate field to the toroidization is proportional to the twist angle. Thank you.